Okay, so last time we looked at a curve and we said, so we studied this tangent vector t. Okay, so we've got three unit vectors, the tangent, the normal, and the binormal. And last time we looked at this tangent vector. Okay, it's a unit vector that points in the direction that is the tangent of the curve at each point along the curve. Okay, so for a straight line, we saw this tangent vector was constant. Okay, it always points in this direction and it's a unit vector, so it's constant. But for a more general curve, as we see, the tangent vector changes along the curve. Okay, so this means that there's a quantity, the change in the tangent vector as we move along the curve. Okay, this will be non-zero. Okay, and we call this the normal vector. Okay, and we now introduce this parameter kappa, okay, which is the curvature. Okay, so this is just a definition for now. Okay, so this is the curvature, and this is the normal vector. Okay, and this is the change in the tangent vector. Okay, so to make progress, let's think about the following. So let's have a lemma. Okay, and the lemma is, let's have a vector A, okay, that depends on some parameter t. All right, and the lemma is if the magnitude of A is constant with respect to changing t, then the following is true. The dot product of the derivative of A with respect to t with A equals 0. Okay, A by dt is perpendicular to A. Okay, or mutually, or orthonormal, or orthogonal, I should say. Okay. Okay, so we can prove this easily. Okay, let's think about the length of the vector A. Okay, so the modulus of the vector A is constant. So this is the modulus of A. It's equal to, well, we can think about the modulus squared. Okay, so if the length of A is constant, then the length squared is constant. Okay, and this is just equal to A dot A. Okay, and this is a constant in this case. Okay. Therefore, we can do d by dt of this thing. Okay, and this is a constant. So it's d by dt of A dot A. Okay, and because it's constant, it equals 0. Okay, so the rate of change of the length of the vector with t is 0. Okay, but this we can write using a product rule. This is dA by dt dotted with A plus now A dotted with dA by dt. Okay, and it doesn't matter the order that you take the dot product of two vectors, especially when it's the same vector A here. Okay, so this is just twice A dot dA by dt, okay, or twice dA by dt dotted with A. Okay. So remember, the dot product is just the magnitude of one, the magnitude of the other, cosine the angle between them. So it doesn't matter if it's these two vectors or we swap them around so that their order changes. Okay, a dot b is the same as b dot a. Okay, so this is the proof. We found that dA by dt equals 0. Okay, so this will help us in what comes next. Okay, so we just saw that if a vector A, if its magnitude did not change in time or with this parameter t, then the dot product of dA by dt and A was 0, okay? Or that this vector A was perpendicular or orthogonal to this dA by dt. Okay, so let's apply that here. So we'll see that dt by ds is perpendicular to t, okay? Because remember, the magnitude of t is 1 always, okay, by definition. Okay, t, n, and b that we're considering are unit vectors. So this is true, okay? So dt by ds is perpendicular to t. Okay, which means that n, the normal, is perpendicular to t. Okay, just as we intuitively expect. If this is the tangent at this point, then the normal will be perpendicular to it. Okay, perpendicular, but we don't know which direction yet, but let's draw it this direction. Okay, so this is the normal vector, it's a unit vector. And we can say one more thing. We can say that the magnitude of dt by ds, okay, so this is not a unit thing, okay, this has some magnitude. It equals the magnitude of this right hand side, so this is kappa, okay, the Greek symbol kappa, and then the magnitude of n, but n is just a unit vector, so this is just 1. Okay, so we find that dt by ds is equal to kappa. Okay, so this is the kind of definition of the curvature. Okay, so this n, this normal vector, is perpendicular to t. Okay, n and t. And if we take the magnitude of this, then we find that this curvature is the magnitude of dt by ds. Okay, so this tells us, this is a measure of how quickly the tangent changes along the curve. Okay, in other words, how curvy the curve is. Okay, so this is one curve, maybe we have another curve like this. Okay, and here the tangent changes very quickly relative to how the tangent is changing here. Okay, so in both those cases, the curvature will be different. Okay, and let's see that in a bit more detail now. Okay, so let's now try and get a better feel for this curvature quantity by looking at an example. So let's think about the curve that looks like this. Okay, and at any point on a curve, at any, like if you zoom in on a section of a curve, then it's best approximated by the arc of a circle. Okay, so here, let me draw the circle that describes this. Okay. Okay, this is called the osculating circle. Okay, it kisses the curve. Okay, and kiss is related to the Latin word osculare. Okay, so it kisses the curve. Okay, and let's think now about 2 points. One at t. Okay, and we'll think about the tangent at this point, t of t. And let's move time on a little bit more, and we get this point, and the tangent here is t of t plus dt. Okay, so this is a circle of radius r. Okay, so we're going to think about this dt by ds in terms of the parameter t, okay, because that's what we're changing. So we know that dt by ds we can write as dt by, and remember that ds is r prime of t, magnitude dt. Okay, so this is 1 over r prime of t dt by dt. Okay, so we want to think about how this tangent changes with respect to the parameter t. Okay, so there are two triangles here. There's this one, r, and then ds. So r, and this is ds. Okay, and let's call this angle alpha, just for the sake of it. Okay, and sorry, this point should be on the circle. So I've drawn my circle badly. Okay, okay, so these points are on the circle. Okay, this is the center of the circle. Again, there's another triangle that involves the two tangents. So we've got this tangent t of t, it's a vector, and then this one t of t plus dt. Okay, so this guy here is dt. Okay, and it turns out that these are similar triangles, so this angle alpha is the same as this angle alpha. Okay, and to see they're similar triangles, let me draw it bigger. So we have this r, and we've got the ds. Okay, and at this point we've got the tangent, which is at 90 degrees. Okay, and then the other tangent is like this. So this is t at t, and this is t at t plus delta t. So if this angle is alpha, then this angle here is 90 minus alpha. Okay, or pi minus alpha, let's say. So this is pi minus alpha, which means that this angle is alpha, and this is the angle between the two tangent vectors, this thing, okay? Okay, so we've got two similar triangles, and of course, we're always thinking about this angle being small. You know, these are small lengths. Okay, so we can think of this as an isosceles triangle, and likewise this. And if we just do the cosine rule on these two triangles, then we get that ds, okay, so this little length, divided by the radius of this osculating circle must be the same as dt, the length here, okay, divided by the magnitude of, so the length of one of these, t, okay, which is equal to dt, because this is just 1. Okay, so therefore we find that dt by ds magnitude equals 1 over r. Okay, but this dt by ds is nothing other than our curvature. Okay, so we find that here our curvature equals 1 over r. Okay, so the curvature is inversely proportional to the radius of this osculating circle. Okay, so this means that small r large curvature and vice versa. Okay, so this curvature is, as you expect it to be intuitively, it is a measure of how curvy the curve is. Okay, so here's a gentle curve. It will have a large osculating circle. Okay, so the radius will be large, so this has got small curvature. Okay, small kappa, compared to something like this. Okay, kappa will be larger along this curve. Okay, and it's a local quantity in that there's a kappa here, there's a different kappa here, a different kappa here, a different kappa here. Okay, because the circles are of different sizes at each point. Okay, but that's curvature and the normal vector. All right. Okay, so let's just finish off. We found the tangent vector, t. We considered how the tangent vector changes along the curve. That's this dt by ds. And we defined a normal vector, n, by this equation. So the change in the tangent vector along the curve is equal to some quantity, some number, it's a scalar quantity, curvature. Okay, this is a Greek symbol kappa. And this vector, which is the normal vector. So this n is a unit vector, but this thing on the left-hand side isn't a unit vector. So we saw that if we take the magnitude of both sides, then we get kappa equals the magnitude of dt by ds. Okay, this is the curvature, because this is a unit vector. Okay, so the magnitude of n is 1. And we know that we can write this as 1 over the magnitude of the derivative of r with respect to t, dt by dt. Okay, magnitude. Okay, so if we're going to calculate the curvature, then this is the working formula that we can use. Now, we didn't talk about what direction this normal vector points. Okay, so if we go back to this curve, then at this point, our tangent vector is along here. And we know that our tangent vector is perpendicular to our normal vector. Okay, because of that lemma from before, we know that dt by dt is perpendicular to t. Okay, and dt by dt is in the same direction as dt by ds. So if this thing is perpendicular to t, then dt by ds is perpendicular to t, and dt by ds points in the direction of n. Okay, so n is perpendicular to t. Okay, so our normal is perpendicular to this tangent. Okay, and it can either be perpendicular in this direction, or it could be perpendicular and pointing in this direction. Okay, but if we look at our circle, this was our tangent at t, the tangent vector at little t, and then we increased t and got a new tangent vector to t plus dt. Okay, and this is the change in the tangent vector as we go along the curve. So in this case, the normal points towards the center of the circle. Okay, and we call this the center of curvature. Okay, so n points towards the center of curvature. Okay, and if we want to find a working formula for this normal vector n, okay, so if you're given a curve r of t, okay, and you're asked to work out the normal vector, then what do we use? We can say that this vector n is in the direction of dt by ds, okay, and that's the same as the direction dt by dt. Okay, so n is in the direction dt by dt, okay, as we've just justified above, and it's a unit vector. Okay, so all we need to do is divide this thing, which is in the right direction, by its magnitude, dt by dt, and we get a unit vector. Okay, so this will be our kind of working formula. If we know r as a function of t. Okay. Okay, so everything's defined in terms of s, but in general, our curves won't be defined in this natural parameter s, but just some other parameter t. Okay, so we always want to think about how we get from s to t. Okay.